All right, I'm going to do a quick little lesson on the conservation of energy, mostly kind of going to go over the concept here. So if I have a roller coaster that is going over a first hill here, so let's say it's the first hill of the roller coaster, and so that's going to be position 1. Okay, so that's why I have the potential energy at position 1 plus the kinetic energy at position 1. Then here we have the roller coaster speeding along, and this is going to be at position 2, that he's going over the next hill, and so hence the subscript of a 2 under the PE and KE. All right, so at each position, regardless of where he is, so we could have the position 2 instead could be somewhere, let's say right there. So at this location, he would have the PE plus KE at this location, so we would just consider whatever the height is at this location. So that's your height in comparison to what the height is here. So this would be the height at position 1, this is the height at position 2, and so on. All right, so let's put this guy back where he was. So generally speaking, the question that might be asked is, what is the velocity when going over hill 2? So basically what we're going to say is that the potential energy at position 1 plus the kinetic energy at position 1 equals the potential energy at position 2 plus the kinetic energy at position 2. So very often the way it will work out is that let's say going over the first hill, the kinetic energy is virtually 0, so that gets canceled out. And let's say we take this guy and we call this position 2. At a situation like that, I might say that this is a position of relatively 0, and so then that means that the potential energy at position 2, that would be 0 in that case. In that case, it would become really simple. So we'd have the mgh, that is at position 1, equals the 1/2 mv squared, that's at position 2. And the mass didn't change, it's the same mass, so that would wind up canceling out. And we get a fairly simple end result. Multiply each side by 2 and take the square root. So that means the velocity at position 2 would equal the square root of 2gh. And that's so long as the potential energy at position 2 is 0. If the potential energy at position 2 is not 0, well, let's back things up. Okay, so I'm just going to undo what I did. And so we're saying that, hey, we're going to put this guy back here. Now there is potential energy at position 2. Now we can take this approach a couple of different ways. For one, we can say that the mgh at position 1 is equal to the mgh at position 2 plus the 1/2 mv squared at position 2. Again, the masses do in fact cancel out. And now we just need to account for that height. So let's say, just for fun, let's say that this is a height of 20 meters, and let's say that this is a height of 40 meters. All right, so then this value here would be 40, this value here would be 20, and of course g is 9.8, and we would just go ahead and rearrange to solve for the velocity after. And so I'm sure that you have the algebra skills to go ahead and work your way through that. Otherwise, there is a little bit of a simpler method. All that really matters is what the relative height change is. So, in fact, I can maybe back things up a little bit further. What if I want to make it so that way I can go back to where was I? Nope, not that far. Hold on, almost there. Maybe I'm not. Screw things up too much. Okay, so I want to make that 0 as much as possible. So again, if this is 20 and this is a value of 40, then who's to say that this isn't, who's to say that this isn't actually a position of 0, because that's all relative. Let's say I want to make this my 0 position, then this would simply be a negative 20 meter position down here at ground level. Okay, ground level would be a negative 20 meter position relative to this line up here. So if I make this my 0 position, which I'm allowed to do, I can make it wherever the heck I want. So then that means that relative to it, let's shrink that. That's no longer 40. This is now 20 meters relative to my 0 position that I've established. So I can go ahead and not worry about this. I don't care about where the ground is. All I care is that relative to this position, that is a 0 position relative to this 20 meter position up here. So again, now I'm able to cross out that potential energy, and as we said before, the velocity would turn into the square root of 2gh, where the h is actually, in this case, it's really delta h. It's the height change, and so that's going to be as long as it's a drop, this velocity will be an increase in velocity. We could run this guy into the opposite direction. So let's say I just, for fun, I flip this guy around. So that too looks weird, but you get the idea. So what if instead this guy is going from right to left, and he's going very fast, and he's going to go up to this hill and go the other way? How fast will he be going over that next hill? He's of course going to be going slower. You hope he's moving fast enough to be able to get over that hill. We would take the same approach. The PE plus KE here is equal to the PE plus KE here. Okay, and so from that we can find the velocity or whatever else it is that we need to find. And one more thing before I go is I'm going to say this, is that whatever the velocity is at this height here, I can say anywhere at this same height, as long as there's no friction and dissipative or non-conservative forces, then when this roller coaster is at this same height and position over here, it'll be going the same velocity, because the change in height or the change in potential energy is the same, so therefore its kinetic energy is the same. All right, so hopefully that was helpful in actually calculating some of these problems, and you guys have a good one. See you next time.